I wanted to start this video with this really beautiful shot of Uranus that doesn't just show us the planet, but also its elusive rings. Because as you probably know, all giant planets in a solar system contain some kind of a ring system. And naturally, Neptune has them as well, as you can see in this image by the James Webb Space Telescope. And even though we know so much about Uranus and Neptune based on a lot of observations from these telescopes, there is obviously still so much we don't understand. Because unlike Jupiter and Saturn, Uranus and Neptune have never really been studied by any probes except for that one flyby by Voyager 2 back in 1980s. And so, hello wonderful person, this is Anton. Today we're going to discuss some additional discoveries about these two mysterious planets, possibly teaching us a little bit more about what happened to these planets as they migrated across the solar system, discover what's inside these planets, and more importantly, how they seem to form their strange magnetospheres. Because by themselves, these planets are not just gas giants. They're known as ice giants for a reason. These two planets, unlike Jupiter and Saturn, which mostly contain hydrogen and helium, are actually predominantly composed of things like oxygen, carbon, nitrogen, and sulfur. Here's roughly what their size and their composition looks like, and though they obviously have some hydrogen and helium on the surface, inside these objects, scientists believe there's a mixture of stuff, including things like methane, which is of course carbon and hydrogen, but also things like water, which is hydrogen and oxygen, ammonia, which is nitrogen and hydrogen, and even some kind of a rocky core right in the middle. And so on average, hydrogen and helium is most likely just 20% or even less than that of the entire planet. But even though we call them ice giants, the reality is probably a little bit more complicated based on the effects we observe on the surface. As in, they're not really made out of ice, they're actually made out of things that become supercritical at very high pressures and very high temperatures. And for many years, based on various models, it was always assumed that there was probably a lot of superionic water, and possibly ammonia, somewhere above the central rocky core. And it's because of that water that they're actually called ice giants. But because it's supercritical water, and very likely supercritical ammonia, they obviously have very different effects. Interestingly, by mass, it's believed that each of these planets contains approximately 50,000 times more water than planet Earth. And so these two planets definitely deserve the moniker ice giant. But in some of these recent studies, one of which you can find in the description, the scientists realized that, well, it's quite likely that these planets, as they were forming, possibly absorbed a lot of planetesimals and various cometary objects such as the famous 67P Churyumov-Gerasimenko. And we actually know their composition pretty well. They're usually very rich in carbon. And if they're rich in carbon, it means that we can probably find a lot of carbon inside Uranus and Neptune, which most likely combine with hydrogen to form methane. And so by running additional simulations, the researchers behind one of the recent studies realized that these planets also probably contain a lot of methane in a very strange, mushy state, basically forming some kind of a thick layer between the hydrogen layer and between the water layer. And so in essence, there's probably another layer that's missing from these images. And this methane would be in a state we've never seen it before, possibly acting like some kind of a liquid snow. And there might be a lot of it here as well, up to 10% by mass. But discovering methane by itself is maybe not unusual. What is unusual is from a different study that also suggested that as these planets were growing, and also as they were basically moving across the solar system, during the period known as the early migration, they very likely disturbed a lot of objects on the way, which possibly resulted in a lot of different collisions. And we actually know that they definitely migrated based on observations from a lot of trans-Neptunian objects. For example, this object, a binary system known as Mors Somnus, or basically a kind of a binary minor planet, has an orbit very similar to Pluto, like a lot of other objects, which we usually call Plutinos, and it has a very stable orbit connected to Neptune. The only way this binary system could have actually stayed binary and acquired such a stable orbit is basically if, back in the days, Neptune very slowly migrated toward the outskirts, slowly capturing many of these objects in a specific orbit without disturbing them in the process. And so many of these orbital connections can only be established if Neptune moved to this location, shifting objects around and locking them in place for billions of years. And because we know of thousands of such objects, currently this is the best confirmation we have for the early planetary migration. And so as Neptune and Uranus were moving across the solar system and migrating to their current location, they most likely disturbed a lot of other rocks and a lot of other asteroids and a lot of other minor planets, which very likely initiated early planetary bombardment. But in case of Uranus and Neptune, they most likely received an overwhelming number, with the study right here basically suggesting that they could have been receiving a somewhat larger asteroid, approximately 1 kilometer across, every single hour for at least 1 million years, although the more likely number is 3 objects per hour. And that means that after 1 million years, they most likely increased the mass of these objects by up to 0.35%, or possibly even larger. And so these studies basically suggest that a lot of decomposition, the atmosphere, and possibly internal structure inside these objects was possibly a result of this extreme bombardment that transformed them chemically, first enriching their atmosphere, but also producing a lot of heat that is probably even still there today, explaining certain heat anomalies. Although I guess more importantly, this would dramatically change their upper atmosphere, and is maybe even the reason why Neptune looks just a little bit different from Uranus. Now it doesn't look as extreme as in some of the older pictures, like the one right here from a few years ago, because as you might have learned in one of the recent videos, this was actually by mistake, and this mistake took decades to fix. You can learn about the true color of Neptune in one of the videos in the description. Either way though, the slight difference between Neptune and Uranus, especially in the upper atmosphere, could be the result of these early collisions, or at least that's what's assumed from these recent studies. But then there is another really important mystery about ice giants that's extremely difficult to explain. The mystery of their unusual magnetospheres. Now normally, a magnetosphere around a planet, even a gas giant, should look something like this. This is what it looks like around Jupiter, and this is the largest planetary magnetosphere in the entire solar system. Here we have clear magnetic lines, north and south pole, and all of this kind of looks more or less tidy and more or less orderly. A very similar phenomenon obviously exists around planet Earth, but we know that they're produced through very different means. On Jupiter, this is probably the result of hydrogen turning metallic at very high temperatures and pressures inside Jupiter. And by turning metallic, it starts to produce electromagnetic fields. In contrast, inside Earth, we actually have iron-nickel alloys that rotate very slowly, and by conducting electricity, they convert energy of electrons into the magnetosphere around the planet. And so the effect is maybe somewhat similar, but I guess just a little bit different. They both involve metals. It's just on Earth it's iron-nickel metals, but on Jupiter and on Saturn it's hydrogen that becomes metal because of very high pressures. But for both ice giants, this is not the case at all. Here's actually what the magnetosphere of Uranus looks like over time. Notice how it seems to rotate and shift around, and is also not really in the center, seems to be tilted, and is basically just kind of weird overall. And something very similar seems to exist around Neptune, as you can see from this simulation by the Royal Astronomical Society. And so the question is, what's really happening here? Why such difference, and why do ice giant magnetospheres look so extreme? Well, the assumption was always that it was not really because of metallic substances or metallic hydrogen, which we don't think exists inside these planets, but instead it was actually formed by some kind of an ionic liquid. And inside of this liquid, it's the ions inside the fluid that seem to carry the charge in a somewhat unusual fashion. And because the liquid itself is not conductive, and the ions don't move as fast and as much, they somehow manage to create somewhat unusual and somewhat hectic magnetospheres. For example, here it's tilted by up to 59 degrees and is constantly moving around and shifting compared to anything we see around Jupiter or planet Earth. But we don't actually know what liquid it is. For many years it was always assumed to be maybe ammonium, and specifically it would be ammonia ions, but the actual mechanism was maybe a little bit difficult to explain. But this recent study that as always you can find in the description decided to actually focus on something else. What if it is water, and specifically water that we know can exist here on Earth, but in extreme conditions becomes even more extreme? For example, we know that sometimes water can acquire an extra proton, or basically it can create what's known as H3O+. It's usually produced by a process known as protonation of water, but technically exists in nature and even exists in outer space. For example, many of these hydronium atoms or hydronium ions have been discovered in the Orion Nebula. And so basically here you have oxygen and 3 hydrogens, but it does have a positive charge. But using a somewhat similar principle, the researchers behind the recent study wanted to find out if you can actually have something more extreme. What if you basically put this under more pressure, more temperature, and give it even more hydrogen? Well, it turns out hydronium can then become aquodiium, or basically H4O, an ionic water with two extra hydrogens, or technically two extra positive charges. And so when the researchers ran the models of high pressure and high temperature, they realized that this can easily exist inside Neptune and Uranus. Moreover, these unusual ions would be strong enough to reproduce similar magnetic fields that we observe around these objects in real life. And so even though hydronium can technically exist on Earth, and even outer space, aquodiium seems to only exist at high pressures and high temperatures, and could potentially be the source of these unusual, unpredictable magnetic fields. And so here, with temperatures of over 3000 degrees Celsius, and at 1.5 million atmospheres of pressure, aquodiium seems to form quite easily and maintain its stability. And we believe these conditions definitely exist inside Uranus and Neptune, at depths where we do find water deposits. And because, as I mentioned before, there's about 50,000 times more water than planet Earth, even if just a fraction of this water turns into these ions, it can definitely produce all of these effects. And so here it's obviously not the entire ocean underneath, it's just a small fraction, but if this is correct, by measuring these magnetic fields, we can maybe figure out the structure of oceans underneath and find a way to scan these planets by measuring the minute changes in the magnetic fields. But naturally, to do any of this, we would have to have a probe orbiting these planets for at least a few years. And so basically here, once again, it's time to ask for someone out there, a space agency, to possibly send a probe to Uranus or Neptune, because they're definitely needed. These are the only two planets we haven't explored pretty much at all, and these are obviously two really strange planets hiding a lot of secrets that can potentially help us explain so much about the solar system and the formation of planets in a lot of other star systems out there. Especially because, as we know from recent discoveries, Neptune-like and Uranus-like planets seem to be exceptionally common. And so naturally studying them would be very important. But I guess for now at least, that's all we have. At least for now, we're basically just limited to observations from a distance, studies involving modeling, and possibly looking at some of the older data from the Voyager 2 probe. But that's just not enough. And so hopefully in the next few years, someone might finally announce the mission to one of these planets, or maybe even both of these planets, in order to help us solve a lot of mysteries once and for all. But until then, that's pretty much all we have. I'm sure we're going to have more studies about Neptune and Uranus in the next few months, so definitely subscribe if you don't want to miss those videos. Also check out some of the previous videos in the description that talk about discoveries from the last few years. On that note, thank you for watching, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.